All right, let's look at some sequences, and this is just a brief overview, some basics, and this is to in the spirit of what's coming in the future for AP Calculus BC students when it comes to series convergence and divergence. If you want to print the sheet to follow along and take notes, you can go to this bit.ly link down here. And let's look at some sequences. First, the definition of sequence, and I'll Googled a few definitions, just try to make this as mathy as I can. And I decided to go with my own little personal definition of sequences. And I'm calling it a function whose domain is the set of whole numbers. A sequence really is just any arrangement of individual terms, and you're simply listing them. You're not adding them or multiplying them or anything like that. It's just an arrangement of certain terms. And typically in calculus, we are dealing with whole number for the domain. So you plug in things like 1 and 2 and 3 and 4, but you wouldn't plug in like 2.5. So I have a couple of very basic sequences here, and I just want you to write the first 5 terms, and all you will do, unless otherwise stated, we'll start at 1. So I'm just going to plug in 1 for n all the way up to 5, and you have your first 5 terms of the sequence 1 over n. That is also a harmonic sequence. Here we have it's ultimately a geometric sequence, negative 1/2 to the n power. And as I plug in my first 5 whole numbers, you have negative 1/2 to the first, second, third, fourth, fifth, and it does clean up to negative 1/2, positive 1/4, negative 1/8. And you can see that. So there's how to generate a sequence if you have the formula for it. And we will be dealing with factorials a lot in BC as well. Factorials in statistics or in counting, it is the number of ways you can arrange this many items. So let's say I have 5 books on a shelf, and I want to know how many arrangements of those 5 books. It would be 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. And an important tidbit for 0 factorial, that is defined to be 1. And if you think about arranging something, if you don't have it, well, I guess you can arrange that 0 item by just not having it. There's the 1 arrangement of it being absent. And so that is 0 factorial. Let's see, moving on. We will be simplifying factorials quite a bit, and it's definitely easiest to simplify factorials not by computing each piece and then reducing the fraction, but by looking at something like 6 factorial over 3 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1. And the 3 factorials will cancel out, leaving us with 6 times 5 times 4. And 6 times 5 times 4 is 30 times 4. That will be 120. And I'll do the same thing with 8 factorial and 12 factorial, except instead of completely expanding it, I'm just going to take that 12 factorial, 12 times 11 times 10 times 9 times 8, and everything after that will be 8 factorial. So my numerator is 8 factorial. Those 8 factorials will cancel, and then you're left with 1 divided by 12 times 11 times 10 times 9, and that is 11,880. So we end up with a reduced fraction of 1,000. What did I say? 11,000? Yeah, 11,880. And we will be in calculus simplifying factorials where we have n's. They're not like actual numbers. And to do this, my numerator is larger than the denominator. So that's the one I'm going to expand out, just like I expanded the 12 until I got to that 8 factorial to match the numerator. So I'm going to expand this one, and n plus 2 factorial would be n plus 2 times the number just before that, which will be n plus 1, times the number just before that, which would be n, times every number before n, which would make that n factorial. The denominator is n factorial. I can cancel these factorials, leave me with just n plus 2 and n plus 1. So there's simplifying those factorials. I didn't mean to undo that. There we go. All right. And then we will also be looking at weird arrangements of geometric series and sequences, and we have to be able to simplify these. And the way we will simplify these types of situations where the only location of the n is in an exponent, everything else is a constant. So what I'll do is I really want to get it to where I just have like 2 to the n or 5 to the n or something like that. Well, 2 to the 2n, or maybe it's not going to be 2 to the n, 2 to the 2n is the same thing as 2 squared to the n, and 5 to the n plus 1 is the same thing as 5 to the n times 5 to the 1th to the first, and then 2 to the squared, that will be 4 to the n over 5 to the n times 5, And then that can be rewritten as 1/5. So I'm taking that 5, and then I'm going to group the 4/5 and write that as 4/5 to the n power. And then just a preview of what's coming. The reason we would want to do that is because this is a geometric sequence, and the geometric sequence will always have a ratio that is the constant raised to the n power. So my ratio, my R for this series would be 4/5. And it's beneficial. We use the ratio a lot in other questions later on in the unit. So that's why I want to rewrite this into a more traditional geometric setup. And we'll have a full lesson on geometric series later. I'm just kind of teasing you with that right now. And I'm going to do the same thing for number 9. We have 5 and 2 as our bases. The only location of exponents is in the of n's is in the exponent. So I'm going to start by changing 5 to the 2n plus 1 to 5 to the 2n. I'll leave it like that. 5 to the 2n times 5 to the first. The denominator is going to be 2 to the first times 2 to the negative 3n. I'm going to go ahead and grab that 5 over 2 that does not have any n's in it. I'm going to separate that out. And then I have 5 to the 2n is 25 to the n. 2 to the negative 3n, I think I may move that up to the top and make that 2 to the positive 3n. Is that okay? Yeah, that's okay. I can do that. And so I have 5 over n. 25 to the n. 2 to the 3n is 8 to the n. And I can combine the 25 and the 8. I can make that 25 times 8 all to the n power, which will be 5 over, why do I write 5 over n? That's a 2. What am I doing? 5 halves, 5 halves, 5 halves. And then 25 times 8 is 400. That's a big ratio. So I, again, got it to the point where I had a number to the n power. Makes it easier to identify the ratio in the geometric series or sequence. And then we will be spending a lot of time talking about convergence and divergence of sequences. And later on, we're going to be camping out on series. A sequence will converge if the individual terms approach a finite number as n goes to infinity. A series is going to be a lot more difficult, and I'm not going to talk about the series in this lesson, but I have 3 different sequences down here, and I'm trying to determine if these 3 sequences converge. And for a sequence, it's very convenient. It's a very nice way to determine if a sequence converges. You simply do the infinite limit of the formula for that sequence. And so I'll do the limit as n goes to infinity, the limit as n goes to infinity of this sequence. And the first one is going to be the easiest one. Because my top and bottom degrees are equal, you can divide their coefficients. This sequence converges to 2. The individual terms converge to 2. Or converges, I guess the series or sequence converges to 2. Number 11, do the same thing. It's the limit as n goes to infinity of e to the n over n to the 4th. And if you try a direct substitution, you will get infinity over infinity, which is indeterminate. We could channel our inner L'Hopital rule here, and I'm going to do this. I'm really going to anger the gods with the way I'm going to write my work. But I do know that as I do L'Hopital's rule, I will differentiate top and bottom individually until I escape that indeterminate form of infinity on top and the bottom approaching infinity as well. My first round of L'Hopital's rule is going to give me the function e to the n over n to the 4th, noted 4n cubed. I still have infinity over infinity. So I go again. And my next round of L'Hopital's rule is e to the n over 12n squared. Still infinity over infinity. My next round of derivatives, e to the n over 24n. Still infinity over infinity. My last one, e to the n over 24. And finally, after my 4th iteration of L'Hopital's rule, which again, that written work is absolutely atrocious. Please, if you're taking the AP exam, don't do that. I'm just feeling my way through the problem. But my numerator is now going towards infinity, and my denominator is a constant. So this is blowing up. This diverges. This limit is approaching infinity. Therefore, the sequence diverges. And it just so happens that you are allowed to just memorize that if n is going to infinity, an exponential function e to the n is going to absolutely obliterate that n to the fourth on bottom. This is a very top heavy fraction. This e to the n is much stronger than the n to the fourth. So that's going to determine the behavior as n gets infinitely large. And so this is going to blow up towards infinity. And that is okay for you to just know that. You don't have to go through the 4 iterations of L'Hopital's rule because that I'm just going to erase that. That really, really scares me how ugly that is. And I'm afraid the gods of math are going to come find me in my sleep tonight. But that is a very top heavy function. And I think I may just write that top heavy because as n goes to infinity, e to the n is absolutely obliterating n to the fourth. And I'm going to talk about that in more detail on the next slide. The last one here, this one's a little bit trickier. I'm going to grab this and give myself a little bit more room to work on the next page. Here we go. So as I work this one out, what I'm going to do to feel my way through this one, and it's because L'Hopital's rule is not really an option. My numerator of factorial is really powerful. Factorials are incredibly powerful. But on the bottom, we have this weird hybrid of a power / exponential function. And I don't know the hierarchy of those two as far as which one is super duper powerful. The bottom, I think, is ultimately going to win. As a matter of fact, I know it will. But let's see why. If I were to expand this out, n factorial means I'm starting at 1, and I'm going to multiply that by 2. Then that times 3. Then that times 4. Then 5. Then 6. Then 7. Then all the way up until I get to n minus 1. And then I get to n, right? As n goes to infinity. My denominator, n to the nth power, means I'm multiplying n times itself a whole lot of times. And my son just showed up, so this is going to get interesting here as I finish this video. Okay, I think I was expanding the denominator. So n to the n power means n times n times n times n times n times n. And we're going to have the same number of n's here as we have in the denominator as we have terms in the numerator. So that's going to go on, and we'll have an n here and an n here. And if you look at this, as this thing is going to infinity, I'm doing the limit as n goes to infinity. At the end, I have exactly equal to 1. And this is pretty close to 1. N minus 1 over n is pretty close to 1. But over here at the beginning, I've got terms that is essentially 1 over infinity. This is 2 over infinity. This is 3 divided by infinity. All of those at the beginning are crashing to 0 very quickly. Crashing to 0. And those zeros at the beginning are powerful enough that this little paltry 1 at the end doesn't matter. This limit's going to be 0. Therefore, the series converges to 0. Right. And I think that was the last one on the sheet, last example on the sheet. However, I am going to add a couple of extra little facts here that may help you out as you are dealing with limits. The first one is kind of what I use to think about this limit of e to the n over n to the fourth, where I said the top is really powerful, more powerful than the denominator. And there is a certain hierarchy of functions that you can just know how they behave in relation to each other. And when it comes to the strength of a function, a logarithmic function is the weakest. A logarithmic function is very weak. A power function, so n to any number power, now that is only true for p's that are greater than 0. So if you have like n squared, n to the first, square root of n is n to the 1/2. But if you have a positive exponent, a power function will beat a logarithmic function. An exponential function will be a power function as long as the base of that exponent is greater than 1. And a factorial will beat all of them. And this is true for situations as n goes to infinity. So as n is getting infinitely large, there's your general hierarchy. So if I have a limit as n goes to infinity of 14 to the n power over n factorial, well, I mean, I know 14 to the n power is pretty powerful, but a factorial will destroy that. That's a very bottom-heavy fraction. That's going to go to 0. And then a couple of limits that would be good to memorize. These are limit definitions of E that show up later on as we do convergence tests with infinite series. The limit of 1 plus 1 over x to the x power is E. And more generically, the limit of 1 plus a over x to the bx power is E to the ab. Those will be good to memorize. They can be proven with a form of L'Hopital's rule that involves your power form, indeterminate forms. But it's easiest and definitely fastest to just remember those two essential formulas for solving those limits.